Hey guys, welcome to another episode of Electronic Savvy. This episode two is a continuation episode for the last episode we discussed yesterday, where we designed a constant current LED driver, basically as a back of a napkin calculation. So now in this episode, we're gonna introduce that same circuit into LTspice. It's a simulation tool that we use to simulate analog digital, circuits to give us another kind of an extra layer of certainty that this design will work in real life, right? So this simulation tool is very handy. We use it a lot in the industry. So I highly recommend you guys following these episodes on LTspice. I'm sure this will come handy at some point in your career. If you guys are in school, this is going to be helpful for you. If you're already in an industry, this will also be a really handy tool. All right, so today we're going to talk about some of the basics, which mostly geared towards the same circuit we discussed yesterday, the first episode, constant current LED driver. But if you guys are interested in do these type of videos, please let me know. Leave a like, comment, and subscribe, and I'll make sure that I post more of these videos. So yes, the way that it works is, for LTspice, we basically just go, when you download it, it's a free software. You could just go download it on Google. The first thing that pops up is this screen. And then here, the first thing you do is just go here, hover on the top left corner. When you hit new schematic, this sort of a new sheet pops up where you can place components, or AKA your circuit, right, on here. So as you guys recall, we had this circuit from episode 1 where we had that kind of a voltage source, we had a resistor, we had 2 NPN transistors to control the current and make sure that we have a constant current flowing through an LED, right? So here we're just gonna walk you guys through the steps. So the first thing is, we're gonna go over here, the component, right? When you hit it, you could basically just type whatever you want. Let's say, LED, you could, type whatever resistors. It'll basically, as you type it up, it'll show you the most relevant part that exists in LTspice library, right? So in this case, let's say, we want this resistor. So, you can see it kind of, hovers around, and you could use your scroll wheel on the mouse to kind of, zoom in and zoom out on the sheet to kind of, make it a little bit easier if you want to move things around. So let's say, we want to place this resistor, right over here underneath, right? And then if you recall, we had another resistor on the base of the transistor. The way that we do it is, so right here, as you can see, when you press the first one, you can still, place more resistors. But now let's say we want to rotate it, right? The way that you rotate is using this shortcut on your keyboard. It's Control and R, Control R. When you press it, it'll basically rotate it 90 degrees every time you press it. And if you want to flip a component, for example, 180 degrees, like, actually just, flip it, like you mirror it, basically. It's the same thing, except it's with E. So it's Control E, right? And this is the default options on LTspice. I actually haven't changed it. We can have another video where I can show you guys how to change every single shortcut. So it's kind of a little bit more intuitive for you, for example. But this is a default. So Control E is just a flip. So now we're flipping it right over here, and then what else we need? We need the transistor, right? So again, same thing. We go to the component section, and then we type up NPN, right? And then it just pops up NPN right over here. Same circuit as episode 1. And then we're gonna place it, let's say, right over here. And then if you recall, we had another transistor, which was a sort of a current control transistor, right? We had it right over here, basically that connects the collector of this Q2 to the base of Q1. But we had it flip, right? So now again, we're gonna do Control E to flip it. And then we placed it, let's say, right over here. And we also had an LED. So let's say an LED, we're gonna press it right here. LED, let's say we're gonna put it right over here somewhere. And then we also had, so any circuit, a side note, any circuit on LTspice needs 2 essential things to actually be completed or actually be at a stage where you can simulate. The first thing is a supply. So you need some sort of a supply, right? Again, the same thing applies. You go to component and then you put, let's say I want like a voltage source, right? So for a voltage, you just basically have this little, voltage supply. You click OK, and then, again, same thing, kind of hovers around. you place here. Let's say we want to have 2, right? Because we also have that MCU input to the base of Q1. And we also have ground. So ground is another component to have a complete circuit in LTspice. LTspice does not simulate any circuit if it doesn't have a ground connection. So, or basically your return connection, right? So let's say for ground, there are 2 ways. Obviously, you could just go here, hover around. It has a ground, so you could just hit that, or you could just hit G on your keyboard. Again, these are default options on LTspice. If you hit G, you have ground. So you want to put ground on the negative terminal of the V1. Same with V2, and same as basically these 2, this resistor, and this transistor, Q2 transistor. So now that's it. So now we have all the circuit, all the components. So all we need to do is just connect them, right? So we just take the wire, we kind of connect this through here, you connect this through here, connect the transistor, connect the resistor. You could actually just kind of go through it. LTspice automatically sort of fixes that, so it's fine. So it doesn't like draw over the component. And then the same thing is here, yeah, same thing over here. Oops, I went a little too far. Got a little too excited there. And then we're gonna connect it over here, and boom. All right. So, and as you guys recall, I said that for example, let's talk about this R2 section for this side. But actually, right before that, let me name these power supplies. Okay. So over here, there are 2 ways. The first way is you could just literally just trace this supply directly to this LED, right? This will work fine. The other way, which I like, which is kind of a little bit cleaner, is to hover over this terminal, and then, or any other basically wire on this LTspice circuit. You could just hover over it, right click, and then hit label net. See this label net. If you hit label net, you could just type whatever you want. It's just a net name, right? So let's say in this case, we called it VCC in episode 1, so we're gonna keep it consistent. VCC, and then we're gonna place it right over here. And the same thing. So it just says that VCC, so as you place it, it kind of giving you an option to move it around. So this VCC, it means if I place this VCC anywhere on the circuit, it means that I'm physically connecting these 2 points on this schematic sheet via a wire, obviously, but not it's not visually there, but physically it's connected. So VCC right over here. And as you guys recall, for this supply, same thing. We call it MCU, right? Let's call it MCU. It's not a big deal. Here, same thing over here for the base of Q1, right? Basically turn on this Q1 transistor. Again, if you guys want to kind of understand, the actual math and the circuit design behind this, please watch out. Please go check out my first episode. I talk about the calculations and the circuit design. So here for MCU, I mean, let's just call it 5 volts. We're gonna select 5 volts, DC value 5 volts. And then for VCC, you can select anything, right? Let's call it 12 volts just to keep it conventional, I guess. So one quick note about voltage sources on LTspice is if you, again, what I did is just right-clicked on this supply, and then when you go to advanced here, right over here, when you click advanced, you have a bunch of options in the functions, right? So right now it's none. It just means that it's a purely DC source. But LTspice does allow you to create pulses. It does allow you to create sine, exponential function, sort of pulse width modulation kind of files and profiles. But the ones that I mostly use is pulse and sine. So for pulse, you could create like just square wave. You could create triangular wave. You could create trapezoids. So many different types of waves where they could have different shapes. It could have different on and off times. As you can see, you could just fill this out over here. In like so many different parameters that you could tweak. Same thing with sine wave for AC signals and things like that. We can definitely talk. We're going to talk about some of these in further episodes. But for now, I mean, again, for this simple circuit, we're just going to keep it simple to DC. So you're going to have 12 volts. And as you guys recall, for R2, I mentioned that it's not really necessary, again, because it's connected directly to an MCU. So microcontroller GPIO pins usually don't source that much current, usually at most 10 milliamp. So it really doesn't matter to keep it's really not that important to keep a resistor in there. But again, for the sake of this simulation, we could basically put any resistance value, like let's say 1K. just to be safe. But this could be just a, do not populate or like, DNP type of component as well. And for R1, as you guys recall, we calculated that number, right, to be about like 20 ohms, right? So that was for about 30 milliamp of constant current through this LED, right? If you guys recall, we calculated that because of the 0.6 volt drop across transistor Q2, in order for us to ensure that there will be a constant current through this LED, no matter what the VCC is, we calculated based on Ohm's law that R basically equals V over I, based on the voltage 0.6 divided by 30 milliamps of current will get 20 ohms. So this will ensure that it'll be about 20 ohms for 30 milliamp of forward current through this LED. And then so the last step is to actually find the right NPN, right? I mean, and this NPN won't work as it is because this is a generic part, right? It's not really a real model. So what we need to do is similar as what we did for other, for the other sections. So we basically just again hover over it, right click, and then this dialog kind of pops up, and then you pick new transistor. You select this, pick new transistor, and I mean, again, for the sake of simplicity, we're gonna select the first one. But as you guys can see, there are like tons of them. There are like tons of transistors that LTspice already has in the library. And again, LTspice, you usually get updates for LTspice every couple of weeks. So they actually update these lists every couple of weeks. So you get like the the newest or the most used models on LTspice. And again, there are ways that we could introduce third-party parts that are not supported in LTspice. I could have another video on that, but for now, just to keep everything simple, I'm going to select the the most well-known NPN, which is 2N2222. For this simulation, as you can see, just kind of glancing through it, you can find out that the collector emitter voltage is 30 volts. So, the collector current is about 800 milliamp, and again, we're way below that number, so we should be good to go. So we select that again. You can just double click it. And then here we select, this part. So now LTspice knows that you're using this specific part number. So it basically takes it as a real model and it simulates around that. And so again, in order to keep things, easier, for interpretation, and also just to make sure that, we keep the parts count low and, keep the, complexity low, we're going to select the same NPN transistor for this guy, for Q2. So we're going to do the same thing. We're going to select 2N2222, and there we go. That's it. So we got transistors by the resistors. Last thing is just the LED, right? For the LED, same thing. You just right click, pick new diode, and then you could select the right LED. And again, just to make sure this will work with every diode. It's just a diode, right? But again, just to kind of make it as close to a final design as possible, we're going to go through this list of diodes and find an LED. So here we have an LED, right, where we have is a kind of a breakdown voltage. Here just in kind of forward voltage. Basically, that's it's a breakdown voltage for like the Schottky diodes and Zener. But for LED, breakdown here just means forward voltage. So the forward voltage of this LED is like 5 volts. But again, the average current is about this one is like about 30 milliamp. So it's kind of pushing it, right? It's at the limit. So let's pick something that's a little bit, I guess, beefier. It can support. It can drive. We can drive this LED a little bit more than 30 milliamps, let's say. So let's go with this Fairchild LED TTLP 690C, where it supports up to 160 milliamp, and it also has a forward voltage of 5 volts, right? So we're gonna select this guy, and you guys wanna boom, we have this. And again, as I said it in my first episode, for this LED to actually work, we need to make sure that we're at least 5 volts. Again, this is a simulation; it works with 5 volts, but so this VCC has to be at least 5 volts. But in real life, it's best to keep it at least at 5.1, 5.2 volts, just to ensure that the variation in different types of LEDs, we call it LED binning, won't really affect the performance of the LED, right? So now that we have this, so the circuit is done. And now what we need to do is to simulate it, right? So the way that you simulate it, you just go over here on, again, top right corner on this kind of a run icon. And then when you hit it, it basically asks you, okay, so how do you want me to simulate it? LTspice is asking you, you want me to run a transient analysis? Do you want me to run an AC analysis, DC sweep, noise, operating point, or DC transfer? So the simplest simulation for LTspice to run is .op. We call it. It's just an operating point. What it does is it basically just calculates the numbers, like the values for the current, the voltage, and all that, without showing you any graphical representation. So you won't actually see anything pop up in terms of a graph, in terms of a plot. It doesn't plot anything. So it's the fastest to run. But in this case, obviously, we want something just to see, right? We want to see that how this circuit actually works. So we want to use transient analysis, which is the most straightforward and the most common one for most of our DC circuits, right? For AC circuits, for filters, we use a lot of AC analysis. We use like DC sweep for Bode plots and things like that. So for this circuit, again, because it's a simple circuit, what we're trying to say is what this transient analysis means is I want this circuit to run for a certain number of time, for like a certain number of seconds, let's say, right? I want it to run for as long as I say it, which in this case, let's put it 100 milliseconds. Right? I want this circuit to run for 100 milliseconds, right? You could put anything, you could put like 10 seconds, but it has to wait kind of 10 seconds or like a little bit less. So it's just better to just keep it simple. We just want to prove that our design works. So we have 100 milliseconds, and then the other block here is time to start saving data. What it's saying is it doesn't actually simulate the circuit until you basically until like let's say 10 millisecond time frame, right? So if you don't put anything here, it starts simulating at 0 second. If you put like something, like let's say 10 millisecond, it'll wait until the 10 millisecond and then it starts simulating the data. Which is, again, in this case, it's not really necessary, right? We just want to kind of see how the circuit works from 0 seconds. And the maximum time step, it just means that what is the increments that you want this circuit to kind of, this simulation to step through? Do you want it to go every 1 millisecond? Do you want it to go every 2 millisecond? But again, that's also not super necessary in most cases, because you could just zoom in, zoom out, or play around with the time scale if you want to find something, right? So in this case, again, we're going to keep it simple. We want the circuit to run for 100 milliseconds and then stop. So that's what we're going to do. We're going to hit OK, and then here the transit comes up, and then the simulation is run. So there are two kind of views for LTspice. One is like this, where they kind of stack it up on top of each other, where it's good enough. But for most of our designs, at least personally, I like to go over here on the window, little a section over here, and then when you press it, like just left click, when you press it, you could just hit. There are like different options. You could cascade them. You could tile them vertically. You could tile them horizontally. Right now it's horizontally. We want it vertically. I like it vertically, so I just kind of do vertically. And then now you see that we have a little bit more room. It's a little bit more visible to see what's going on. And again, you could just kind of drag these two windows. Like let's say for the circuit, I could just kind of drag it to the left. And then and again, as I said it, you could use your scroll wheel to kind of, go up and down to zoom in, zoom out. But the easiest way is just kind of go up here and then hit this little zoom full extent, sort of a, icon over here, and then it'll basically full zoom it to the full picture. So see, now we have like the full picture of the circuit. And what we can do is kind of drag this other window, the plot window over here, so we have more room to see what is going on in the circuit. So as we said, we want to basically just test how much current is going through this resistor, right? So it was right now. If you just click on it, you see this little guide that kind of as you hover over the circuit, you see that there is that little icon that pops up. This is basically a current probe. So you could, what it's saying is if you press it, it'll plot current through this resistor. The other thing is you could hover up like outside this resistor, like right over here when the kind of a little lighter blue line is. This is just a wire. So for wires, what LTspice allows you to do is you could plot voltage. So this red kind of a pin is just a voltage probe. This guy that kind of looks like like a fly or something, it's a current probe. And then this guy is a voltage probe. So if you press it, it just shows you the voltage. See the voltage here, as we said it, as we basically calculated was about 0.6 volts, right? At 0.67 volts in this case. But again, we kind of mainly interested in the current, right? Because we want to make sure the current through LED is constant. So again, we want to like plot this guy, plot the current, and again, this should be very similar to the current through LED. Again, there will be some leakage current, like some imperfections, but ideally, I collector is is equal to like the I emitter. So in this case, if you press it, you see that you have pretty much the same. I mean, there is obviously some changes between the collector and emitter current because of like the structure of BJTs, but normally it's not significant. So we just kind of assume that IC equals IE basically. But as you can see, the current through this LED, as you can see here, like D1 denotes this LED. So ID1, it means the current through D1 is the blue one. So it's like about 34, right? So about 34 milliamp. And again, that's kind of the current that comes from VCC. And as you guys recall, we kind of talked about it, but this I emitter, again, because it's an NPN transistor, it's always going to be basically E, like I collector, which is in this case the current through the LED plus the current from the base, right? That's what this arrow really showing is like this current. The collector current is always the summation of this current plus this current, right? The emitter current plus the base current. And again, because like I said, because in most cases base current is very negligible, it's very small amount. Again, when you're dealing with like amps of current, it really doesn't really show up. But again, because we're dealing with a small amount of current in this case, you could see the difference. But yeah, so that's pretty much it. And then what we said is, let's just test, right? I mean, the idea was if we change VCC to any voltage, the current through this diode, through this LED must stay the same. Let's see if this is the case. So if you go here again on this V1, the VCC, if you just right click, and then instead of 12 volts, let's just put like 24 volts, right? When you put 24 volts, let's see if the current changes. So we go here again, we have to rerun. So every time you make any adjustments, any changes to the circuit, you have to rerun it. So we just rerun it. And as you can see, it's exactly the same current. I mean, I think it was like 22, it's a little bit higher. Obviously, because of the actual more voltage going through here, the more current through the collector, there will be slight variations. But as you can see, it's very negligible. So again, we ensured that even though we doubled the VCC, the current through this LED stayed the same. Thanks to this circuit where kind of creates that closed loop feedback, where we ensure that the current through this LED always stays within a specified range, which was defined by using this R1 resistor. And also, just as a side note, since we kind of confirmed this, one thing that you guys should do, looking through your LTspice simulations is, for example, let's say we pick this guy to 2N2222. What you can do is you could actually go to, to your, let's say, Chrome, let's say in this case, and there's this website I really like. It's called Octoport. I mean, no sponsor, but the way that you do it is just basically search for any part that you want, and then they show you all the distributors that sell this particular transistor, this particular part, with all the stock availability and the pricing. So let's say in this case, we found this part is 2N2222. Again, 2N2222, as I said, it's a kind of a series of transistors that are very, very identical in a sense, in terms of like the functionality. So but there are couples manufacturers that actually build it. So in this case, let's say we go to DigiKey, right? If you select DigiKey, it's gonna pop up, or and then here we can actually see the data sheet. So it's probably just gonna have me. I already downloaded this, so I'm just gonna open it up real quick right here. So yeah, so as you can see, this is the transistor, right? Just to make sure that our understanding was correct, right? This is the data sheet. If you guys scroll down a little bit more, there are like bunch of attributes for this transistor. But if you scroll down, we're mostly interested in um, there we go, the base emitter voltage, right? That's what we kind of talked about. That we said that the base emitter voltage is usually around 0.6 to 0.7 volts. For this particular transistor, the BE voltage, the base emitter voltage, can go all the way up to 2 volts at 500 milliamp of collector current, right? So that's why I said that the higher, the kind of the larger the collector current, kind of we have like some variations in the base emitter voltage. But again, for this simulation, the most typical value is about 0.7 volts, and as you guys saw, we did simulate it in LTspice, where it showed that this voltage, this voltage over here, which is the basically base emitter voltage, because the emitter here in this case is grounded, right? So the base emitter voltage for Q2 was about 0.7, right? About like 0.6, 0.7 volts, 680 millivolts. But yeah, so that's it for today. I mean, this episode, again, we want to kind of walk you guys through how to take the circuit that we calculated using back of a napkin calculation. We actually designed that circuit, found the resistor values in episode 1. How can we take that design and simulate it just to make sure that our design works and our understanding is correct? We took that design, we put it in LTspice, and we simulated it so it verified that our understanding of our circuit is correct. The values we calculated was correct. And then this is a very, very handy tool. I highly recommend you guys learn a little bit more about this. And again, if you guys like to see more videos of like this, please leave a like, drop a comment, let me know in the comment section, please. I love to make these videos. I just want to make sure that I make a kind of a video that you guys are interested into watching, right? So thank you so much again for watching through this video. Please don't forget to leave a like, drop a comment, and subscribe. Thanks a lot for watching. Bye-bye.